right. Good afternoon, guys. We'll get started. So last time we said we'd go away from the idea of propositional logic, at least for the time being, and move on to predicate logic. And we introduced the idea of universal quantification. And that was a shorthand way of stating that some propositional function, some predicate, was true about every object in this thing called the universe of discourse that we defined. All right, so that's an example of one kind of quantifier. There's another kind of quantifier, and that's called the existential quantifier. So the thing we're going to talk about next is existential quantification. Oops. Quantification. All right, so the universal quantifier specifies that something is true of everything in the universe of discourse. The existential quantifier specifies that something is true for something in the universe, where something means at least one thing. Okay, so given a propositional function, let's say px, the existential quantification of px is another proposition. It's the following proposition. And that is that px is true for at least one value x in the universe of discourse. Px is true for at least one value x, or object x, in the universe of discourse. All right, that's what that means. We write the following thing, a backwards e, and then x, because x is the object I'm talking about, and px, which asserts that the proposition p is true of x. All right, and we say there exists an x such that px. So I would say exists an x such that px. That's how I would read that. This symbol, the backwards e, is called the existential quantifier. All right, so we've seen two of them. We've seen one that looks like an e for exists and one that looks like an a for all. All right, so last time we observed that the universal quantifier was essentially shorthand for conjunction, right? If something is true of everything in the universe of discourse, it's true for the first thing, and it's true for the second thing, and it's true for the third thing, and so on. Just in the same way, the existential quantifier is also shorthand, but it's shorthand for disjunction. It's shorthand for a sequence of many disjunctions, possibly infinitely many disjunctions. So this notation is essentially a shorthand. So if your universe of discourse consists of the objects x1, x2, x3, and so on, well then exists an x such that px really just means px1 or px2 or px3 or and so on. Of course, this isn't really shorthand if the universe of discourse is infinitely big, because then, I mean, yeah, it's a short way of writing it, but there is no alternative unless you write for infinitely long. So you should notice that because this quantifier is essentially a shorthand for disjunction, we know that it's going to be true as long as at least one object makes it true. And this matches up with the definition of the proposition it corresponds to, which is always nice. So since it's essentially a disjunction, it's a disjunction of many things, it's going to be true when the predicate is true for at least one object in the universe of discourse. Okay? And on the other hand, it's going to be false if the predicate is false for all objects in the universe of discourse. Okay, so keep straight where it's true or false compared to when I say for all or for at least one. Okay, that's important. So let's do some examples. Here's one. Let's let px be the propositional function x is greater than 5. Well, in that case, so first we specify the universe of discourse. The universe of discourse is the set of integers. So all integers, positive, negative, and 0. The proposition exists in x such that px, well, that's going to be true, right? Why is it true? Yeah? Right, there's at least one integer bigger than 5. 6, for example. P6 is true, therefore there exists an x such that px must also be true. So it doesn't matter that P3, for example, is false. That's okay, that doesn't ruin everything. The important thing is that there's at least one x that makes it true. 6 is an example. There's infinitely many more, right? 7, 8, 9, 10, and so on are all perfectly good examples. Does that make sense? All right. So let's talk a little bit about some notation issues. I want to talk briefly about the binding of quantifiers. And this is important to understanding how to write things out. So just like negation, quantifiers apply to the smallest complete thing after it. Right? Remember we said last week that negation binds very tightly. So too do quantifiers. So as an example, if I wrote down exists an x such that px and qx, you might think this is a perfectly reasonable thing to say. Right? As we'll see soon, you can combine these things together using the rules for propositional logic, right? Because each one of these things is just a proposition. For all x, px is a proposition. So we can use it in conjunctions and disjunctions and so forth. So this is an example of doing that. The important thing to understand is, as I've written it, x is only meaningful here. Right? So what this really means is this is the same thing as exists an x such that px, all in brackets, and qx. And the x outside the brackets, the x in the q, that doesn't mean anything because I haven't told you what x is. If you think back to the first lecture when we were talking about what counts as a proposition, I said if you said something like 3 plus x equals 5, that's not a proposition because you don't know what x is. Well, the same thing happens here. Qx isn't defined because x isn't defined. Right? We don't know what x is. So you need to be very careful when you are writing these propositions that your brackets are as they should be. So whenever you write for all x or exists an x, that x is only valid for the smallest complete thing after it. And if you want that complete thing to be bigger, you need to add in brackets. Is that clear?
Yep.
All right. So if you did want to write this, you would have to write exists an x such that px and qx. That is how you would write that. If you wanted to assert that there was some value x such that px is true and qx was true at the same time. All right. What you could write is this. You could write exists an x such that px and exists x such that qx. That's different because now it's syntactically valid. This makes sense to talk about. Is this the same thing as that, though? Are those equivalent ideas?
No.
No. Why not?
Because you switched the sign.
Because I switched the sign. So what do you mean by that?
When you put it in, you have to switch the sign.
So I think you're thinking of something related to De Morgan's law.
Yep.
So that's not the case here because there's no negation. Yeah.
X might mean different.
Yeah, so x is just a variable. And if you want to think about this in terms of like a programming language or something like that, x's scope is the stuff immediately after it, the smallest complete thing after it. So for this first one, that's that alone, and then the scope is over. And for this one, it's that alone, and then the scope is over. All right? So to understand this fully, let's do it as a little translation exercise. If px meant, I don't know, x is even, so the universe of discourse is all integers, px means x is even, and qx means x is odd, well then, which of these is true or false? Yep.
First option would be false because the and is impossible.
Right, there's no number that's both even and odd. So this first thing on top is going to be false.
However, the second one would be true.
The second one is true because this says there exists a number, an integer, that's even, and there certainly is such an integer. And the second one says there exists an integer that's odd, and there certainly is such an integer. So the very first one, this one on top here, this is saying that there exists an x and px and qx is true of the same x at the same time. The second one, this conjunction down here, it's just saying that there's a number that has this property and there's a number that has this property. They could be the same number. In this particular case, they're not because there is no such number. But it's not requiring that they're the same. And that's an important distinction with scope. All right. So just as an example, if px means x is even and qx means x is odd, where my universe of discourse is the set of integers, well, in that case, exists an x such that px and qx is false, but exists an x such that px and exists an x such that qx is true. And finally, exists an x such that px and qx, that's meaningless. Right? That's not a proposition because you don't know what that second x is. It's not saying anything. Right? There's no value that can be plugged in there. So if you understand these three lines, then you understand what's going on so far, and that's good. Yeah?
Is the third x on the bottom line meaningless because the universe of discourse is not defined for it?
The universe of discourse is defined, but there's no quantification for it. So I would need to say for all x qx or exists an x qx, or put that in brackets somewhere so that one of those earlier ones applies to it. Other questions? Yeah?
Does
Yeah, so everything I said in this example would apply just as well for all. Other questions? All right. So, now that we know that, let's talk about the next thing, which is negating quantifiers. So as you can see from the last example, we're starting to bring back all of the symbols like conjunction and disjunction that we had before. The next one we're going to bring back is negation. And some interesting thing happens when you negate a quantified statement. So how do you negate a quantified statement? So let's think about that. Let's do an example to sort of inspire us. What is the negation of the statement, all people like math? What is the negation of that? Yeah?
Not all people like that?
Not all people like math. Okay. Good. So when is that true? If we were checking to see if this was correct, when would we know? Yeah? So that's another common answer. So all people dislike math. That's another common answer. Yeah? Sure.
If there exists one person who doesn't like that.
So that's for this column here. So that's the same thing as saying there exists one person who does not like math. What about on the other side? All people dislike math. When is that true? Yeah? Yeah, there does not exist a person who likes math. So that right there should tell you that in fact these two things are not going to be the same, right? This statement that all people dislike math is not exactly the same as the other statement. All right, so that's good. Let's keep that in mind and do another example. What's the negation of at least one person likes math? What would the negation of that be? Yeah. Not one person likes math. So when would that be true? Yeah? All people dislike math. So all people dislike math. Okay, great. So let's think about these two examples. So in the first example, we had an all, right? And remember, all means for all. And what we ended up with was there exists and a negation. So exists and negation. In the second example, we had at least one. And at least one means exists, right? At least one, that's our definition for exists. And what we ended up with was all and dislike, which is basically a negation, right? Because the original thing was like. So those are the two quantifier negation rules. So I'll write them out explicitly. The first one is the negation of for all x px is logically equivalent to there exists an x such that not px. And it works the other way too. The negation of exists an x such that px is exactly the same as for all x not px. Right? That's exactly what the two examples we just did say. Does anyone see an easy way to remember this rule, if maybe you only remember propositional rules for some reason? Yeah?
Is quantification related to and or is not quantified?
Exactly. So remember that for all is basically shorthand for conjunction. So if I negate a conjunction, then I get a bunch of ors that are all negated. That's De Morgan's rule. And that's exactly this. Exists is a bunch of ors, and everything that's ored is negated. And it works in the other direction too, right? Exists is a bunch of ors, and if I negate a bunch of ors, I get a bunch of ands, and they're all negated. So really, quantifier negation is just applying De Morgan's law to the longhand version of what these quantifiers mean. That's all that's going on. All right? So let's do some examples. So the negation of for all x, x squared is bigger than x. And the universe of discourse is all integers, say. What would the negation of this be? So I want the negation of for all x, x squared is bigger than x. Notice that I'm really defining a propositional function here. I'm just writing it explicitly every time. So what would the negation be? Yeah?
For at least one x squared is not bigger than x?
Yeah, so for at least one means exists. And you said it is not the case that x squared is bigger than x. That's what you said. Now we can simplify this a little bit more because we have more than just a general propositional function. We actually have the meaning of it and we can reason about it mathematically. So what's the negation of x squared is bigger than x? Right, x squared is less than or equal to x. It's very common to forget the equal case, right? The opposite of greater than is not less than. The opposite of greater than is less than or equal to. Right? That's a very common source of confusion. And of course, I need my parentheses there. All right. So what about another example? And that's the negation of there exists an x such that x squared equals 2. So I want the negation of exists an x such that x squared equals 2. What would that be? Yeah. Right, so if we do that symbolically, we get for all x, it is not the case that x squared equals 2, which is really just for all x, x squared does not equal 2. Right, the negation of equals is does not equal. All right, so that's how you would solve those two. Is it clear to everyone when things are true and false in terms of these quantifiers? All right, so just to make sure, I'm going to give you a little table that will hopefully help you. So this is the negation I'm interested in. The negation exists x px is equivalent to for all x not px. And the negation is true if for every x in the universe of discourse, px is false. And the negation is false if there is at least one x in the universe of discourse such that px is true. All right, so that's the first row. The second row is for the negation. It is not the case that for all x, px. We know that that negation is equivalent to exists in x such that not px. The negation is true if there is at least one x for which px is false. Oops. And the negation is false if for every x in the universe of discourse, px is true. All right, so if you're having trouble figuring out what's going on, maybe you will find this table helpful. If you don't find this table helpful, just continue what you were doing before. Any questions about the table? Yeah? Such that, or so that. Other questions? All right, so now that we have a good idea of how these predicates work, to fully ensure that we do, let's talk a little bit about translating sentences with predicates and quantifiers. All right, so when you're doing translations, just like before, you want to look for certain keywords to let you know what kind of quantifier you'll be using. So for all, you usually look for words like, words like every or all. Those are the common ones. For exists, you look for words like some or at least one. Those are the two common ones. Some is for existential quantification. That's an important thing to understand. All right, so I'm going to do a bunch of examples, and in all of these, the universe of discourse is the set of all people. So for the next couple of examples, that's what it is. Let's start with every student in this class will learn about logic. All right? Okay, so if we're doing translation, the first thing we need to do is define some propositions. We look at this sentence and we see the word every, which makes us think, oh, this is probably going to involve quantifications, which means I should define some predicates instead of just plain old propositions, right? If there weren't any quantifier statements here, you wouldn't use predicate logic, you just use propositional logic, which we're already good at dealing with. But the fact that it says every means I need to quantify something, which means I'll need some propositional functions. So the propositional functions you would want to define here are what? What should be defined? I see two. Yeah? Yeah. So learn about logic is definitely one of them. Anything else? Yeah. Yeah, student in this class is the other one. And I need student in this class because the universe of discourse is the set of all people, right? And there's lots of people who aren't in this class. If the universe of discourse were just the set of students in this class, then that would be redundant and I wouldn't need it, right? So this is another time where it's important to pay attention to the universe of discourse. All right, so we'll define two predicates, or propositional functions. Sx will mean x is a student in this class, and we'll say Lx to mean x will learn about logic. So everyone seems to agree that these are the two important things. How do we put them together? We know that it says every, so we know that there's going to be a for all x out in front. That seems plausible. How do we finish it? Yeah? Sx and Lx. And I need parentheses there. Any other suggestions? Yeah?
SX implies LX.
Right, so the other option is Sx implies Lx. Any other suggestions? Okay, so someone who thinks that it's the second one, Sx implies Lx, what's your reasoning for not liking the first one, Sx and Lx? Yeah?
With the first one, it kind of implies that for that to be true, everyone in the world must be a student in this class.
Yeah, so think about what this is saying about objects in the universe of discourse. The universe of discourse is a set of all people, and the first translation here, this one, this says that every single person is a student in this class and will learn about logic. Right? And that's too strong a statement. That's a very strong statement. It says things about a lot of people. The statement on the right says, if you're a student in this class, then you will learn about logic. And that's the correct translation of every student in this class will learn about logic, because that sentence doesn't say anything about the people who are not in this class. They might learn about logic, they might not. Right? That's not our concern. Our concern is only about the students in this class. So by using an implication, you're narrowing your sentence as much as possible, which is good because this particular sentence is a very narrow sentence. It only talks about the people in this class. All right? So the sentence on the left says, every person is a student in this class and will learn about logic. Okay? The sentence on the right says, if someone is a student in this class, they will learn about logic. And that is an accurate translation of the meaning of the sentence we were given, whereas this one is not because it's too broad. Right? It says too much. Is that distinction clear? Yeah? No, for this one I wouldn't use an if and only if, because lots of people who aren't in this class could also learn about logic. Right? If you said if you are for all people, if you are a student in this class, if and only if you learn about logic. That's not going to be the same thing, because the original sentence says nothing about the people who aren't in this class, but if I had a biconditional, that would say something about people who aren't in this class, in particular that they won't learn about logic. But that's not the meaning of the original sentence. Other questions about this distinction? This is probably the most common source of errors on assignment 1 and test 1, is this mistake here, putting an and instead of an if. Okay? All right, let's move on. Some student in this class will learn about logic. Hopefully all of you will, but the sentence is just some of you will. Let's assume that we have the same propositions from the previous one, so we still have Sx and Lx. How do we translate this? So some means there's going to be an exists. And what goes inside? Yeah? Sx and Lx. Okay. Any other options? Oh, okay. Implication. Other thoughts? I mean, the only one that's even close to reasonable would be an and, right? So let's also think about this one. Right? We have the same two basic choices as last time. Discuss. Yeah.
I'd almost think that and is more appropriate in this case.
Okay.
For implication, in the case that there's someone that's not in this class, regardless of whether or not they learn about logic, they exist, and because they're not in this class, that statement becomes true. And because you've got the, as long as it's true for one case, that means that it's true even if nobody that's actually in this class learns about logic.
Yeah. It sounds like you're on the right track to me. So think of it this way. If I said some student in this class will learn about logic, do you think that you would be able to point to such a person? Would such a person definitely exist? Am I asserting that there really is a student who's in this class and knows about logic? If I said that. Yeah, right? That seems like it should be the case. At the end of that sentence, we should be able to find someone in the room and say, you're the X that's making that true. All right. So that leads you more towards this. If you go to the sentence on the left, the implication version, are you guaranteed to be able to find such an X such that that's true in this classroom? Well, no, for the exact reason you said. What if nobody in this classroom learned logic, but there's at least one person in the world who's not a student in this class? And there is. So there is one person in the world who's not a student in this class, which means S for that person will be false, which means the implication will be true. So for anyone in the world, any person who is not in this class, this implication will be true. And since there's at least one person in the world not in this class, this is definitely true. But I said that no one in the class learned about logic, and you all agreed that in the sentence, some student in this class will learn about logic, I should be able to point to a student in this class who knows logic. Right? But I can't do that in the first sentence, although I can in the second sentence. So the problem we have here with implication is the opposite of the problem we had with conjunction in the previous example. In the previous example, the conjunction was too strong because it talked about people who aren't in this class. In this example, the implication is too weak because it talks about people who aren't in this class. Is that distinction clear? So this is the second most common source of errors, is confusing implication and conjunction inside of an exists. Okay? So this thing asserts that there really is such a person. But this sentence on the left, there might not be such a person if there's at least one person who's not in this class. Okay, so these two examples are very important. All right. So, as a general rule, you should be suspicious of conjunctions inside universal quantifiers, and you should be suspicious of implications inside existential quantifiers. That being said, you can definitely say sentences that have conjunctions inside universal quantifiers and implications inside existential quantifiers. That can happen. There are perfectly reasonable sentences that have those, but they should sort of set up a warning in your head and just take a second to think, is this really what I mean or what John means because he's asking me the question? Yeah? In the for all, the exists. So this one, so if I say some student in this class will learn about logic, you should be able to find that person somewhere in this classroom, right? All right. So the first sentence on the left, Sx implies Lx, well, if there's at least, so let's say nobody in this class knows logic. at all, but there's at least one person in the world who isn't in this class, and that's true. Well, the sentence on the left, the one with the implication, that will still be true, right? Because Sx will be false for some person because they're not in this class, and that means the implication will be true, and so the existential quantification of that implication will be true as well. That's what's going on there. Other questions? Okay, so to be clear, I'm not saying never put an implication in exists. I'm just saying be careful. Yeah? So usually when you're defining predicates, you do the same thing as with propositions. You try to say a single fact. Or in the case of predicates, it's usually a single property. Yeah, I can see that. So in that case, you would define two, Sx and Cx. And then the Sx you would replace with Sx and Cx, all in parentheses imply Lx, or and Lx in the case of the correct answer. Other questions? All right, so let's do another example. So I'm going to define a few predicates here. Ix means X is an instructor, and Kx denotes X knows everything. All right, so let's work through a few of these. What is no instructor knows everything? What would that translate as? Any thoughts? So this is harder because the keyword isn't sort of staring at us in the face. Yeah? Yeah, it's still the set of all people. Implies K of X? Not I of X implies K of X? Okay, any thoughts on this? Yeah? Okay, other thoughts? Yeah?
I think the first one, that means that anyone who's not an instructor does know everything.
Anyone who's not an instructor does know everything.
Well, that's what the first one says.
Yeah. Okay, so that seems like it's saying something different. Okay, yeah.
Not for all.
Not for all.
Ix and Kx.
Okay, any thoughts on this one? Yeah.
Well, actually, I was going to suggest next one.
Okay, sure, yeah.
Basically, there is not exist, so not exist, Ix and Kx. Because not for all means at least for one.
Okay. All right, any other thoughts? Yeah. Okay. Yeah.
The second last one, both implications
So not exists in X such that Ix implies Kx. Okay, so we have a lot of answers, which is good. All right, so the one I like best is this one right here. So no instructor knows everything is the same thing as saying there does not exist an instructor who knows everything. Right? There does not exist an instructor who knows everything. Does everyone agree that that's the same? Okay. So given that we've translated it in such a way that the quantification is more obvious, now do people believe that this answer here is pretty reasonable? So why wouldn't we have an implication here? Yeah?
There's nothing in the proposition or the compound proposition that there is no implication. It's just stating a fact.
Yeah, it's just stating a fact. I mean, really, you don't want an implication here for the same reason you don't want an implication in the previous example. Yeah?
Well, the other thing is this one, what it's saying is there exists one instructor who does not know everything.
Sorry? The 1, 2, 3, 4, this one?
Yeah.
Okay.
It's saying there exists an instructor who does not know everything.
Right, so the issue is this one here, yeah, so there exists an instructor. There exists a person such that if they're an instructor, then they don't know everything. So notice that if there's at least one person who's not an instructor, then it's automatically true anyway. Right, so that's what I would think is the more serious issue, although that is correct too. All right, so we like this one. There does not exist an x such that ix and kx. But notice that this is exactly the same as for all x, it is not the case that ix and kx. And we already know that that is the same thing as not ix or not kx, right? That's by De Morgan's law. So far, so good. All right, so this thing here is exactly the same as using quantifier negation. Ix implies not kx, right? Which is this thing right here, which means that's good too. That's good because it's the original. And of course, you could also translate this in the other direction, or eliminate or add an implication in the other direction, or equivalently take the contrapositive to get kx implies not ix. And we didn't see that one, but that's another one. Yeah.
So the thing that you translated the last two, the second last one saying
This one?
yeah.
Yep.
That one say for all people, if that person is an instructor, then he or she does not know everything.
Exactly, yes. And that's the same as no instructor knows everything. If you are an instructor, then you definitely don't know everything. Right? That's saying the same thing. And this last one here is saying, if you know everything, then you must not be an instructor, because no instructor knows everything. Okay? So is it clear how all of these are the same? All right. So there's lots of different ways you can think of translating these. Any one of these answers here on the left would be perfectly valid. The other ones here, not so much. All right. The next thing we need to notice is that you are allowed to have multiple quantifiers. Okay? So what that means is you can have a for all and then another for all. Question?
I just didn't really understand why the implication is above her.
Where?
Like the second class.
This one? Yeah, so this is saying if you are an instructor, then you don't know everything. So anytime you have an instructor, you know for sure that they don't know everything. That's what the implication means, if the statement is true. So that's the same as saying no instructor knows everything, because anytime you are an instructor, you don't know everything.
But the implication is still true for anyone who's not an instructor.
Yes, but that's okay. The sentence doesn't say anything about people who aren't instructors. They could know everything or not. Yeah?
Wouldn't it still be false if they're not an instructor, if the date is not clear, if the class is not clear?
So for this one here, if they're not an instructor, then this is false and the whole thing is true. Some other stuff might happen with other people, but that single, I mean, if you view it as a big conjunction, that single conjunct is true. And that's okay, because we're not saying anything about people who aren't instructors. Okay. So multiple quantifiers are possible. So let's let fxy mean x and y are friends. Okay, so notice this is a propositional function that applies to two objects from the universe of discourse, which for our examples here is still the set of all people. What does for all A there exists a B such that FAB mean? So notice I'm using different letters, but it doesn't matter the letters I use, it's as long as they're consistent. What does that mean? Yeah? Yeah, everyone has at least one friend. All right, so the obvious question then is, does order matter? Could I say exists a B such that for all A, FAB? Can I put the quantifiers in whatever order I want? Does this mean the same thing? No, what does this mean? Right, there's one person who's friends with everybody. So the order of your quantifiers matters. That's important. Okay, let's do another example. Let's let mx denote x is male, fx denote x is female, lx denote x is a student in this class, and kxy denote that x knows y. Okay, and again, the universe of discourse is all people. So how would we translate every female student in this class knows at least one male student in this class? How do we translate that? Yes.
For all x, x of x implies, for all x.
Okay, that's okay. Someone else? Yeah? You can, yeah. Yeah, I mean, as long as you're consistent. You can plug in any value. LX.
Implied.
So, no, we're very close. This is good. Who can help them? Yeah.
I would say K, X, Y.
Okay, no, that's good. So what we're trying to do right now is say X is somehow standing for the female student, right? That's where we're going with this because Fx and Lx are both true. And Y, based on what you've told me, seems to be standing for the male student, right? Yeah?
Oh, I was thinking it's starting over,
Okay, let's try to work with this because we're pretty close. So right now we've introduced this variable y, so we need to quantify it somehow. Yeah? Okay, I'll just write that over here. Okay. Yeah, that's okay. So my and kxy, and we also need one other fact, and that's that y is in this class, right? All right. Thoughts about this? Yeah. Yeah, I have an and sitting out here in this for all statement, and maybe that's concerning. So really the two options here are and or implies. Right, those are the only two things that make any kind of sense. What is the first one saying? What is it saying if it's an and? Any thoughts? Yeah?
every person in the female student in this class and
Yeah, so that's enough. It says some other stuff, but right off the top, that's enough to see that we probably don't want an and. Right? If we have an and, then it's saying every person in the world is a female and in this class, and then some other stuff that we don't care about, but we can already see that that's wrong. All right? So that's why we don't want this to be a conjunction. If it's an implication, then we're in pretty good shape because now we're only asserting something about females in this class. And the thing that we're asserting is that there exists a person in this class who's male and that they know. Right? So this here is what I would consider the most natural translation of that sentence. Does that make sense? All right. So let's move on. The next example I want to do is, again, the universe of discourse is all people. And I want Vxy to mean y is the best friend of x. And I would like to translate everyone has exactly one best friend. That's what I would like to translate. So let's try to do that. How would we translate this? Everyone has exactly one best friend. The thing that's hopefully confusing to you, because it's new, is this idea of exactly. Right? That's the thing that's maybe throwing you off. What does exactly mean? Yeah. So it's kind of like an if and only if in the sense that there's these two directions to it, right? Exactly means not less than and not greater than. Right? There's two sides to it, just like there's two sides to an if and only if. So one way to think about questions that have exactly in them is to assert two things, right? You would say, y doesn't have fewer than one best friend. And that's easy because that is just saying that there exists a best friend of everyone. And the other thing you have to assert is that y or x or whatever variable you're using doesn't have two best friends. So you assert that they have one friend, one best friend, and that's not too hard, we know how to do that. And then you assert that they don't have two best friends, right? Because they have exactly one. And if they had more than one, well, they would have at least two. Is it clear sort of what we're going for here? Yeah? Yeah, so I mean that's essentially what we're doing. More than one is the same thing as at least two. They could, but if they have three, then they also have two. Right? If you have three best friends, I can find two people who are your best friends. All right. So the idea is we want them to have at least one, but not two or more. Right? If I can assert both of those things, then it's exactly one. All right? That's important. So let's work through this. I'm saying something about everyone, so that means I'm going to have a for all. And if I'm saying they have a best friend, so there exists a person Y such that they're best friends. So B, X, and Y. Okay. And now I need to say that they don't have two or more friends. There's a couple of ways you can do this. The easiest way I know how to do it is to say there's not a second, which means we also have the case that for all other people, let's say Z, if they are best friends, then Z is actually just Y in disguise. Right? That's really what it is. So if they are best friends, so if X and Z are best friends, then in fact what you have is Z equals Y. So two variables being equal, well, that's a perfectly valid proposition. And this doesn't have the weakness I talked about first class when, you know, x plus 5 equals 3 is not a proposition. X plus y equals 3 is not a proposition. Because z and y are both defined, right? Y is defined here, it's quantified existentially, and z is defined here, it's quantified universally. Okay? So another way you could write this, and this is another common one you'll see, is z does not equal y implies not bxz. Right? That's the exact same thing, it's the contrapositive. It's just like saying if z and y are different, then they're not best friends. Right? That's the same as saying if they are best friends, then they're the same. Yep.
When you say a given variable quantified universally,
Yeah.
is that all you're doing when you do that is like assigning a fact or a characteristic to any one of those variables in the sense?
Yeah, so you can think of that as saying that variable has some kind of defined meaning here. We don't know what particular object it is, but we know how it's being used.
And the defined meaning can be like any proposition.
It can be any object from the universe of discourse. Right? It's being quantified in some way. I'm saying some specific thing about it. Whereas in the sentence x plus y equals 3, I'm not saying anything about x and y.
Right, but the specific thing that you're saying about it is a proposition, right?
Yeah, it's this disjunction if it's existential or conjunction if it's universal. That's exactly what I'm saying about it. So there's no ambiguity. It's just shorthand for a large number of conjunctions or a large number of disjunctions. That's all that's going on. Any other questions about this? All right, so I want to introduce a new thing, which is always best to do at the end of a lecture. And that's the idea of arguments and validity. This is the next step. So we've defined all this stuff with logic, but we haven't talked really about anything interesting you can do with it. Yeah? Yeah?
How would you do like exactly 2?
Exactly. So yeah, you do a very similar thing to this, except you have a bunch more not equals. Right? So exactly 2 would mean there exists one, there exists another one that's different, and there does not exist 3. So it becomes a lot more complicated as these numbers get bigger, because you have a lot of things to keep track of, but the pattern is exactly the same. All right.
Or can't wait to say you want to do 1 million?
No, there's not. So some textbooks introduce various things called uniqueness quantifiers. We don't talk about those here. So, I mean, you can define whatever shorthand you want, but it's only meaningful to you. For this course, there is no shorthand that we can use. You have to do it this way. But of course, on a test, I wouldn't ask you, like, there exists exactly, 1 million or something like that. That's obviously crazy. All right. So we've talked a lot about logic, but we haven't done anything interesting with it yet. The reason we talk so much about logic is because this course has a lot to do with proofs. And proofs and logic are, as you might expect, very closely related. The sort of stepping stone between them is the idea of the argument. So arguments are valid or invalid. Okay? So now that we know how to state things precisely, we're ready to think about putting statements together. And when we do that, we create something called an argument. And a rigorous argument that's valid is more commonly known as a proof. And that's what we'll see a ton of in this course. So that's why we need to talk about that. We need some way of putting statements together using valid rules. So as an example, if I have the premises, if it is cloudy outside, it will rain, and the premise, it is cloudy outside, then I can make a conclusion that it will rain. So does that seem like a valid argument? Yeah, I mean, it seems pretty good, right? And the reason it makes sense to us is whenever you take the premises to be true, then the conclusion follows. So it may or may not be cloudy outside, but if it were, and the other premise was true as well, then the conclusion would certainly follow. Right? That's all it means to be valid. So an argument is valid if the truth of the premises imply the truth of the conclusion. That's what it means for an argument to be valid. So in general, we have something that looks like this. We have the premises, say, P1, P2, P3, and so on up to Pn. These are all just propositions that we know. And following that, we have some conclusion, which I'll call C, which is just a proposition that we know. Well, then if we have that P1 and P2 and P3 and so on all the way up to Pn implies C, well, this means that the argument is valid. It's a valid argument. It's a good argument in some sense. Notice that if you have false premises, then it doesn't really make sense to talk about the argument as being valid or invalid. That's a slightly different issue called soundness, but we're not so worried about that right now. For right now, we'll always assume that the premises are correct, are true. All right, so we can combine these things together to show validity. And we do that using the rules of inference. And this is a lot like what we discussed last class or the class before for the logical equivalences. So we have a bunch of them. And I'll go over them quickly today, and we'll use them next class. So the first one is addition. And the addition says, I'll say what we're given on this side, and what we can conclude here. So addition says, I'll put this on the next line. Addition says, if we're given P, then we can conclude P or Q is true. Right? If I know for a fact that P is true, well then P or Q is also true, because it doesn't matter what Q is. It could be true or false. Yeah?
Oh, what's the rule of rigorous argument? What do they mean for argument?
So a rigorous is more of a qualitative evaluation of the argument. It'll be more when we talk about proofs that we're just going through verbally rather than going back to logic every time.
All right.
Yeah. So that's the first one. We also have the conjunction rule. And here you're given P and Q, and you can conclude that P and Q is true. So if I told you, hey, this fact P is true, and then later on I told you, hey, this fact Q is true, well, you could combine them together to derive that their conjunction is also true. Yeah?
Yeah, can you explain the addition more? I'm not
Yeah, so if you knew for a fact that P was true, well then P or anything else is true, because a disjunction is true when at least one of the things is true, and I'm telling you that this thing is true. Okay?
they all have to
Right, yeah, so this is sort of a stepping stone to that. This will be somewhere in the process you'll do something like this. Yeah, so these might not be an entire premise, it might be part of a premise, or it might be combining other premises to do something else. We'll see lots of examples. Question?
So any premise or anything that's given is always taken to be true?
Yeah, so when we give some examples, it'll be clear, but yeah, the premises will take to be true, and we'll see how combining them under the assumption that they're true leads to the conclusion or not. All right, so that's the conjunction rule. We also have the rule modus ponens. And that's when I am given that P is true and I'm given that P implies Q is true, well then I can automatically conclude that Q is true. Right? This is the example we did just a few moments ago. If it's cloudy outside, then it will rain. It's cloudy outside, and we all agreed that it would rain if we took those premises to be true. Okay, so that's what that rule is. We also have a very similar rule called modus tollens. And this says if you're given two things, if you're given not Q and you're given P implies Q, then you're allowed to conclude, any guesses? Not P. All right. What else do we have? We have the simplification rule. If I told you for a fact that P and Q was true, well then you could conclude that P and Q were both true on their own. Right? If a conjunction is true, then each of the conjuncts has to be true. There's no other way that it could be true. After simplification, we have kind of a weird one called hypothetical syllogism. And it says, given P implies Q and Q implies R, you're allowed to conclude P implies R. Right? So it's kind of like skipping that middle step, canceling it out if you like. This is something related to the idea of transitivity, which we'll talk about much later in this course. All right, we also have something called disjunctive syllogism. And it says if you're given P or Q and you're given not P, well, that disjunction is true, but P isn't. And the only way that can happen is if Q is. Right? There's no other way for that disjunction to be true. They can't both be false or the disjunction would be false. And then the last one for now is a really weird one that we will never use, but I will give it to you for completion. It's called resolution. If you're given P or Q and you're given not P or R, you are allowed to conclude Q or R. And that's kind of weird. The only way for both of these to be true simultaneously is if at least one of those is true. Because this part is going to be false or that part is going to be false, so one or the other has to be true. It's kind of a weird one. I don't think I've ever used it in my 10 years teaching this course. Okay, so what we're going to do next time is make use of these just with propositional logic to decide if arguments are valid. Once we're really good at that, we'll bring in a few more rules for predicate logic and then do it there. All right, so that's it for today, guys. We'll see you next week.